Hi everyone, my name is Rinku. Myself and Priyanka Nayak will give a talk on kernel bypass techniques for high-speed network packet processing. This video is part of the IIT Bombay CS744 course taught by Professor Umesh Belur. The prerequisite to understand this talk is the basic undergrad computer networks course. What do you expect to learn by the end of this video? We will first discuss the journey of the packet from the source application to the destination application and back. Then we will talk about the limitations of packet processing within the kernel and motivate the need for kernel bypass techniques. Later, Priyanka will discuss the concepts of kernel bypass and describe few popular kernel bypass techniques like DPDK, NetMap, and MTCP. Finally, we will take the talk to the next level where we briefly discuss the recent packet forwarding trends. Also, not to forget, there is a follow-up video that deals with the practical aspects of DPDK installation and programming. Good. Since the stage is now set, let us start with the basics. How does a typical packet flow between the source and destination applications? You have already studied that the packet traverses from the sending application towards the network interface, which is then pushed to the wire, whereas the receiving NIC accepts this packet and the packet traverses all the way up to the receiving application via the network stack layers. Sorry to bore you with another known fact. You can see an example TCP packet here. It consists of an Ethernet header, IP header, TCP header, application data, and the Ethernet frame checksum. The checksum allows us to detect whether the packet has arrived correctly or has been corrupted on the way within the network. What are the main contents of these headers as far as this talk is concerned? The Ethernet header consists of source and destination MAC addresses and type that determines the next header. In our case, it is IP. Similarly, IP header comprises of source and destination IP addresses, header checksum, packet length, and a type for the next header, which is TCP in our case. The TCP header comprises of source and destination port or socket address that identifies the application from where the data came or should be delivered, and it also contains checksum. Great. Now that we are done with the basics, let us understand the role of the kernel in traditional packet processing. That is, what happens to the packet once it arrives at the network card of your computer and until it reaches the application. Also, what is the role of the kernel when the application reverts back with a response packet that is sent out all the way back up to the wire? Let us first discuss the receive path. The packet arrives at the network card, which is stored at the hardware receive queue. The NIC matches the destination MAC address with the set of acceptable MAC addresses and validates Ethernet checksum. How does the NIC driver prepare itself for processing these accepted packets? The NIC driver pre-allocates kernel memory buffers where the packets are stored. The driver also pre-allocates the transmit and receive ring buffers within the memory. A ring is a circular queue that is shared between the NIC and the driver. Each slot in the ring stores the length and the physical address of the packet buffer. The accepted packets are processed further as follows. The NIC copies the packet to the memory location pointed by the RX ring slot using direct memory access DMA and updates the RX ring. DMA is used so that CPU time is not spent on packet copy. NIC then generates an interrupt to inform that the packet is received and is available in memory. The interrupt triggered by the NIC causes the CPU to pause or disrupt the process in execution. Therefore, interrupt processing in Linux is split into two parts, top half and bottom half. The top half does minimal processing so that minimal disruption is caused to the running process, whereas the bottom half does the major heavy lifting. We now describe the top half processing. The interrupt triggered by the NIC causes the CPU to pause the current process and switch to the kernel mode for interrupt processing. The interrupt descriptor table is indexed to get the pointer to the interrupt service routine. The interrupt service routine acknowledges this hardware interrupt and schedules the bottom half processing for later, which is processed as a software interrupt. The CPU switches back to user space and continues with the interrupted user process. CPU schedules the bottom half processing when it is free. That is, it services the software interrupt, which is also called as soft IRQ. CPU context switches to the kernel space to service this software interrupt. The NIC driver dynamically allocates an SK buff for the received packet. What is this SK buff? SK buff, also called as SKB, is an important data structure for network I/O processing. SK buff contains the packet metadata like the pointers to the packet headers and pointers to payload and more packet related information. The kernel maintains a single copy of the packet within the packet buffers. If multiple packet copies are required, for example, tools like Wireshark and TCP dump require individual copies, then the skbuff structure is cloned and all the clones point to the same packet in memory. If you want to know more about skbuff, visit the provided link. Let's continue with bottom half processing. The allocated skbuff is updated with the packet metadata. The Ethernet header is removed and the skbuff structure is passed to the network stack. This process is repeated for all the packets in the buffer. Finally, the layer 3 protocol handler is called. L3 or L4 refers to IP and TCP processing here. Both the layers perform certain common functions like matching the destination addresses, whether it is IP or socket address, verifying the checksums, and pulling out the respective headers. The specific functions of layer 3 are route lookup and fragmentation, after which it calls the layer 4 packet protocol handler. When an application opens or binds to a TCP socket, a pair of read-write socket queues are assigned. These queues specify the packets to be sent or received. Layer 4, that is TCP, handles the TCP state machine and enqueues the packet to the socket read queue. Note that the socket queues do not hold actual packets, they hold pointers to the packet. After this, the application is notified that the packet is received. The application issues a read system call, which context switches the CPU to the kernel space. The packet is dequeued from the read queue, copied into the application buffer in the user space, and the skbuff structure is released. After which the CPU returns back to the application, that is, it switches back to user space. Now, the packet has finally reached the application and our receive path ends here. Next, let us look at the transmit path of an application packet. The application that wants to send a packet has to copy the packet into the kernel packet buffer. This is done using the socket write system call, leading to one more context switch. The socket's send function invokes TCP processing. TCP dynamically allocates skbuf structure for the packet and enqueues it to the socket write queue. TCP performs common functions like building the packet header, adding it to the packet buffer, and updating the skbuf structure. TCP then calls the L3 protocol handler, which is IP. Apart from the common functions, IP fragments the packet if necessary and invokes the L2 protocol handler. The queue discipline, popularly known as queue disk, is a scheduler that holds the packets and applies policies like FIFO or priority scheduling. The packet is enqueued to this queue disk queue if the NIC's transmit hardware queue has free buffers. Queue disk dequeues the packet, performs tasks that cannot be performed in hardware, for example, IP or TCP checksum calculations. It then invokes the driver's send function. The NIC driver stops queue disk if the hardware transmit queue is full. Otherwise, it invokes DMA to copy the packet from the packet buffers to the hardware transmit queue and tells the NIC to send the packet. NIC calculates and appends the Ethernet checksum and sends the packet on the wire, after which it sends an interrupt declaring that the packet is sent. The driver then frees the skbuf structure and resumes the queue disk queue. So now we have gone through the packet processing within the Linux kernel for both transmit and the receive path. Now that we have seen the packet processing pipeline, the question is, what are the major overheads for packet processing within the kernel? We saw that there are many context switches for the packet processing of a single packet. This pollutes the CPU cache. Traditional kernel-based packet processing invokes an interrupt for each packet, which costs us time and loss of locality. Dynamic allocation of skbuf and packet copy between the kernel and user space adds to the overheads. Some data structures like the socket read or write queues, TCP accept queues are shared. Therefore, locking mechanisms add to the overhead. Recent NICs provide high speeds in the range of 40 to 100 gigabits per second. The kernel packet processing overheads make it impossible to achieve line rate for such NICs. The network community has provided optimization mechanisms to accelerate the kernel network stack. NAPI or the new API issues a single interrupt for a batch of packets. Generic receive offload GRO combines the packets of the same receive stream so that the network stack processing is done once for the entire packet stream. Similarly, generic segmentation offload GSO is opposite of GRO, where the packet to be transmitted is not split until it reaches the NIC driver. Priyanka will talk about the benefits of multiple hardware queues. For more details on these topics, you can refer the links. The above mechanisms can only reduce the overheads, but not eliminate them. Priyanka will now talk about how these overheads can be eliminated.
Thank you, Rinku. Having a brief overview of the kernel network stack processing, let us now see what are the overheads that have a huge impact on the performance of application, especially which are handling a huge traffic of packets. The first one is the overhead of context switch between the kernel space and the user space that is involved for processing a packet. A small example for this is when suppose you have an application of a client server socket based application which issues a read request. Read is a system call and hence it triggers a switch from the user space where the application is running to kernel space from the where the data would be switched. In fact, this also leads to copy of data from the kernel space to the user space application buffer, which is also an overhead. The next overhead is with respect to memory allocations. Each packet at the NIC is DMA'd into a memory in the kernel. An SKB or skbuf structure points to this packet and also maintains metadata for the packet. However, for each receive as well as transmission of packet, this SKB is allocated on demand. So, this dynamic allocation becomes part of the packet processing in the kernel and is a huge overhead. Also, the interrupt on reception of each packet is an overhead, which is handled now in the kernel using techniques like NAPI. I will be covering the overhead of data structures later in the talk today. But the question that arises is how to overcome these overheads. A solution to handle this is by bypassing the kernel for the network stack processing of a packet. That is, do the entire layer 2 to layer 4 processing in the user space. Let us now see how does this avoid the overheads discussed before. As the processing would be done in the user space, we avoid the context switch to the kernel space. The application and the packet processing components have a common shared buffer and hence the packet copy overheads are also avoided. Next, the memory for these buffers as well as the corresponding structures is pre-allocated and hence the dynamic allocations is also avoided. Before diving in further on these kernel bypass mechanisms, let us understand the different modes of their operation. One mode that they operate on is the interrupt mode where the NIC notifies the CPU that it has packets to be serviced. It does this by generating an interrupt, which is a hardware mechanism. Interrupt, as in the case of kernel, has overheads and it is reduced by generating a single interrupt for a batch of packets. The other mode of operation is poll mode, where the CPU keeps checking if the NIC has packets to be processed. It is a software mechanism as the CPU keeps checking control bits for these notifications. This is a nice mechanism to reduce latency of a packet processing, especially for high-speed data processing applications. But it wastes a lot of CPU cycles for this polling. Two popularly used kernel bypass mechanisms are netmap and DPDK, and they each follow one of the modes of operation. We will discuss them next, starting with DPDK. DPDK is Intel's data plane development kit and is one of the widely used industry efforts for high-speed networking. It consists of a poll mode driver or PMD, which is operating in poll mode. A NIC needs to be binded to this driver to enable DPDK processing on the packets from this NIC. But once binded to this driver, the NIC is invisible to the kernel NIC drivers and hence cannot be simultaneously used by a kernel application. Next up, DPDK has pre-allocated memory called as RT mempool, which consists of huge pages. Huge pages are pages of larger sizes, for example 1 GB, as opposed to the normal page size of say 4 KB. Huge pages are used to reduce the TLB misses and thus have faster memory access. Next, whenever a packet is received at the NIC for the DPDK application, it is transferred into a memory called as RT mempool by the PMT driver. The The memory termed as RT-membuff consists of a packet as well as metadata of the packet, which is similar to the kernel's SKB. A difference between the SKB and the RT-membuff is that RT-membuff is pre-allocated and the metadata and the packet buffers are stored in contiguous memory. This is done to just use a single call to free and allocate these packet buffers and its corresponding data structures. Also, similar to kernel, there is a RT ring which maintains pointers to this RT membuff. One other interesting thing to note is that DPDK works in cooperative multiprocessing. That is, a DPDK resource gets allocated to a starting process called as a primary process, and other DPDK applications running on the same machine share the access to these resources through the primary process. This is great if you have trusted applications running on a machine, but may have some security concerns when you don't have these trusted environment. You can read up more on DPDK in the link provided, and also look up on the follow-up video which talks about programming and running DPDK applications. Next up is NetMap. NetMap, as opposed to DPDK, is not a complete kernel bypass mechanism. That is, it also has its shared memory in the kernel space. However, it is similar to the DPDK, the way the packet transfers are done. That is, it is transferred into a pre-allocated memory, and then the pointers to it are given or shared with the application. But the one interesting thing about NetMap is that it works in a transparent mode. That is, unless the NetMap application is running, the NIC is accessible to the kernel driver, and hence the kernel applications can run over this NIC. That is, these NetMap-based applications can work along with kernel-based applications. You can refer to this link to read up on the research paper on NetMap to get more idea. Now, DPDK and NetMap are good because they bypass the kernel for us and handle the packet processing overheads. But they only provide processing to the layer 2 of the network stack. Then the question is, what about the layer 3 to layer 7 processing? To understand this, let us see the overheads in the kernel pertaining to layer 3 to layer 4 processing and see how they are mitigated in a kernel bypass mechanism. In the default case, the hardware interrupts from the NIC are handled by a single core and then copied into other cores for further processing. However, this involves sharing of data structures like TCP accept queue, socket list, etc. among the cores. This adds overhead of logs while processing a packet. So, what do we need now? We need a user space network stack which can work over kernel bypass mechanisms like NetMap or DPDK and also handle these shared data structure based overheads. A popular stack in this regard is MTCP or multi-core TCP. Now, before diving a bit more into MTCP, let us understand how it requires support from the NIC to achieve this multi-core packet processing. In modern NICs have multiple queues. That is, every incoming packet gets distributed to one of the RX queues. How this is done? This is done using a technique called as RSS or receive side scaling, which is basically a hash of 4 tuples in the packet headers of any packet. That is the source IP, destination IP, source port, and the destination port. The hash returns the queue ID into which this packet will be allocated. So once allocated into a queue, it can be transferred or processed entirely on application running on that core, and that doesn't require any intercore communication. And it can also avoid thus the intercore communications that are involved for the packet transfers. Now, with this as a basis, MTCP leverages this multi-queue NICs to build a user space network stack which is also multi-core scalable. Yeah. It has multiple rings, that is one ring per core at the layer 2, that is the net map and DPDK. And it has per core threads running on event-driven socket mechanism, which was discussed in a prior lecture on ePole. The data structures such as accept queue, socket list, etc. are per core local to have lock-free access. Thus, this avoids the shared data structure overheads. In fact, as the processing is done on a single core, all the data pertaining to a connection can be locally maintained on a core. For further details on MTCP, of its APIs and performance, you can look up on the research paper on MTCP. Now, next up, with an increasing demand, modern networks are built to be highly scalable, scaling up to 100 Gbps. But the question is, are the kernel bypass techniques itself enough, or do they require some additional help? Rinku would talk about what's trending in the networking domain with regards to this. Thank you.
Thanks, Priyanka. So one of the interesting questions to ask is, we have developed high-speed networking hardware, but can our applications utilize these benefits? What should the application programmers do to process the packets within a few nanoseconds or at least microseconds so that we can achieve line rates? Even with kernel bypass techniques, the packets have to travel the network stack in the software, even if the processing is done in the user space. The next interesting question is, can the application packets check out earlier without even hitting the application user space? There is a recent trend where application processing is offloaded from the user space. Tools like BPF, Berkeley packet filters, and eBPF can be used to offload the application process within the kernel itself so that there are no context switches. Similarly, XDP programming can offload the application processing to the NIC driver. Therefore, even SK buffs are not allocated to these packets. More interestingly, recent programmable hardware advancements like programmable NICs and switches allow us to offload packet processing at the NIC hardware, or even better, at the network edge switch. That is, the packets do not even have to enter the enterprise network and are processed directly at the edge. All of this is super exciting. Now, you may have a question. Why did you spend the last 20 minutes explaining kernel bypass if there are better alternatives? Okay, relax. There are limitations on what type of computations can be offloaded. These limitations differ for each technique and for each programmable hardware. For example, BPF can only do stateless processing, whereas eBPF can do limited stateful processing. Programmable hardware have limited memory and restricted instruction sets. Therefore, we cannot offload everything. So, the best idea, as we all know, is to use a hybrid approach, where certain application computations are offloaded to the kernel or driver or NIC or switch, but rest of the computations run as the part of the user space DPDK application. For more details, visit the links. With this, I end our talk. Thank you.